Good morning. So let's start the second lecture. So in the last lecture, we were looking at modes of heat transfer, just sort of an introduction to this topic, and we looked at heat conduction. So today I'm going to start with the heat convection or convection heat transfer. So conduction. Remember that I said conduction is actually a mode of heat transfer that depends on or that works on the principle of diffusion of energy. So it's a random molecular motion that contributes to conduction. Convection basically has two aspects to it. The first aspect is again random molecular motion, which I call diffusion. So there is a diffusion of energy, and the second contributing factor to convection is bulk fluid motion. Now, just for your information, I can share this that when you have both these mechanisms taking place together, we call it as convection. But you will see in your book that when they only talk about bulk fluid motion or heat transfer because of bulk fluid motion, this would be called as advection. Okay, so when I talk about convection, I'm actually going to talk about both aspects, not just bulk fluid motion. So heat convection is essentially the sum of these two mechanisms taking place together. And to explain what heat convection is, let me just take an example. Let's say we have a surface which is at some temperature, let's say Ts, and let's say I'm blowing, let's say, a fluid. Let's for now consider it to be air. It doesn't matter. So we have a fan, and I'm blowing some uh, air over this surface. Let's say the air temperature, which I'm going to denote as T infinity, is less than Ts. So Ts is more than T infinity, which means it's a heated surface, or the surface is hotter than the surrounding fluid which is flowing over the surface. So from fluid dynamics considerations, what you know is that when you have a fluid flowing over a surface, and because of no slip boundary condition, the fluid will actually experience or will start forming a boundary layer. So what we will see is is the formation of a hydrodynamic boundary layer, right? So this is a hydrodynamic boundary layer. So this is pretty well established. You've done this in fluid mechanics. But what happens to the temperature? So very similar to the hydrodynamic boundary layer, we also see the formation of a thermal boundary layer in these systems or in these situations. So the thermal boundary layer happens because you have a temperature which is of the surface which is different from the temperature of the fluid. So what you will see in this case would be the formation of a thermal boundary layer. Okay, and heat transfer now will actually happen through this boundary layer, and this is what I'm going to try and quantify in convection. So how does heat transfer take place in convection? So if you think of it from a physical standpoint, notice that fluid particles which are very near the surface where the velocity is zero, so the particles actually are at rest. So at that location, the transport of energy from the hotter surface to the fluid is because of diffusion, or because of this random molecular motion, because there is no motion. I mean, there is no bulk motion. The fluid is not flowing there, so it is where you start actually getting conduction heat transfer from the surface to the fluid. But as the transfer happens through conduction, as you go higher in the boundary layer, there is the this heat which is coming in, this energy that is coming in. It also, you can think of it this way, that the particles are now moving at a velocity which is not zero, so they convect away or they advect this heat. So the heat is actually taken away by the presence, by this flow. So you have the bulk flow which convects away all this energy, And so that is what I was saying, that this convection is essentially the combination of these two mechanisms. First is you need to have heat conduction into the boundary layer, and then beyond that, once the heat is conducted into the boundary layer, you have the energy being swept away because of this fluid motion. So convection is actually essentially a contribution of these two aspects. And so we have, just to reiterate, we have random molecular motion near the surface, which again is diffusion, as I'm saying. So that is part one. And then the second part I said is that is energy that is being brought in, or energy heat which is conducted into the boundary layer, is swept away by the flow. If there was no flow, then heat transfer will only be because of conduction. But because there is flow, this heat has another way of escaping this uh, this zone. So in most of these conduction, or in most of these convection type analysis, it becomes important to understand how boundary layers form on the surface, both hydrodynamic and thermal boundary layers. So when we talk about convection at some point in this course in more detail, we will actually do bottom up analysis, where we will first understand these boundary layers and their role in giving us, letting us calculate how much heat transfer should we expect from a convection uh, mode. Now there can be different types of convection in practice. So we can classify convection heat transfer modes based on some characteristics. So the first mode that you will see, and which is something that we will always, which will be more frequently used than anything else, this is what is called as forced convection. So as the word suggests, we are going to force the convection mode of heat transfer. And the easiest way to imagine this is that it's actually the same as the earlier problem. So if you have some object, right, at some temperature Ts, and the temperature of that object, and let's say I'm blowing some fluid over this object by the use of a fan or a pump, or it could be a blower. So as long as the temperature of the fluid is not the same as the temperature of the surface, we can carry we'll have some heat transfer, because there is a these two entities are not at the same temperature. So there would be transfer of heat, and this mode of transfer of heat, when you are making or you're forcing a fluid to flow over a body, is actually called as forced convection. So it can be either way around. By the way, let me be very clear. Ts could be more than T infinity, or Ts could be less than T infinity. So you could be either taking away heat from the solid, or you could be, moving heat or supplying heat to the solid. The second case of convection is what we call as free convection, or also natural convection. So natural convection, you may imagine, can be something like this. Let's say you have a hot ball. Okay, let's say you have a hot sphere, uh, which is being heated in a furnace, and I bring it out in the air and I leave it to cool. I don't do anything. I just leave it on the floor and I allow it to cool. So what happens is that when you have this hot sphere when it's in this still air, let's say, so the surrounding is, let's say, air, you will have air coming in contact with the hotter surface, and so you will have a density change in the air, because the temperature of the air next to the surface, next to this solid, will actually increase. So temperature increases, which means density will decrease. Density decreases, and if I say, let's say, gravity is pointing downwards, so we need to be very specific about this, because that is what is going to induce this motion. So if density decreases, you will have the air or air particles with lower density will rise up, and cooler air will actually displace, will take away that displaced volume. So we will have some currents which would which may look something like, we'll have the formation of a plume from the surface of the solid. So we'll have air rising up. So that would be sort of a flow that will be established. But now what this is doing is, because you have fluid rising up, you can now imagine there is heat transfer, and because there is an induced flow because of a density change, we call this as free convection or natural convection, because this happens because of any external uh, means. By we don't have to provide any external power or any external device to induce this motion. So so that is the mode that is called as free convection. So remember, this is because of buoyancy. And what I'm saying is that when temperature rises, we have a corresponding decrease in density, and so the hotter fluid will rise up and induce these buoyant currents in the fluid. So that is the second mode. Now, just to give you an example, by the way, of these two modes in practice, some of you who may have seen, electronic, or even, if you've opened your, if ever you've opened a desktop computer, there was a time when actually most of these desktops were actually made with a fan. There used to be a sink on the processor, and then they would used to put a fan on it, and they still do it. Of course, the designs have changed, but they used to put a fan. So that is an example of forced convection, because you are trying to pull, energy, or trying to pull heat from the hot processor. But then free convection is also one of those things where, uh, very old, when these fans were not those that advanced. Actually, the older processors used to just have a heat sink sitting on the processor. So that heat, that's the sink, as I'm saying, it used to conduct heat from the processor. But then, because it was hotter than the surrounding air, so air used to come in contact with that heat sink and then convect away heat because of natural convection. So this is one of those simplest things that you will see, or a simplest example that I can give, if you may have seen in a computer. If you're not seen, that's okay. We'll take those applications at a later time. The third mode is what we call as mixed convection. Okay, and this is also sometimes called as combined convection. So this mode typically happens if the flow velocity. So this, as I'm saying, it's combined or mixed. It means it's a combination of the two mechanisms of both natural and forced convection. And this typically happens when you have the velocities which you are, maybe, which you're creating because of an external fan or an external blower. If those are not as large as compared to the velocities induced because of natural buoyancy changes. So when you have this combination where both seem to be, where both sets of velocities are nearly the of the same magnitude, or are similar in magnitude, then you can have both modes of heat transfer taking place. So natural, or rather mixed convection, would be one in which both mechanisms are uh, are contributing to the overall heat transfer. Now, the other aspect about convection at this stage that I should mention is that what I've looked out, or what I've explained so far, are scenarios where we only had what we call as a sensible heat exchange. So a sensible heat exchange is one in which you only see a change in internal energy of the fluid. So there is no change in anything else. But what you also should understand is that, so in the internal, for example, in all these cases, if there was air flowing over some object, in maybe air flowing over a solid block, or air rising up over a sphere, In these cases, you know that if I assume air to be a perfect an ideal gas, these energy changes will actually lead to only a change in temperature of the that surrounding air. It will not lead to a phase change. Air will not change phase. It will not turn into maybe liquid gases, or liquid oxygen or liquid nitrogen, if I can say that. Okay, so sensible heat exchange is essentially any change which only causes a change in temperature. It does not cause a change in phase. So this is not related to change in phase of the fluid. But in nature, we also see a lot of processes where there's a change in phase, and those heat exchanges, because of the change in phase, are called as latent heat exchange. So this is because of change in phase. Okay, and where do we see this? This will be typically true in heat exchangers, especially if I take you back to thermodynamics. If you remember a little bit of the Rankine cycle, what you see in the boiler is a phase change process. You are actually causing liquid water to change phase and become steam or water vapor. And in the condenser, you would see another phase change process where steam is actually being condensed into liquid water. So these two processes, boiling and condensation, are what comprise this latent heat exchange. And so, just to take an example of, let's say, boiling. So let's say you have a pan in which you are boiling water. So boiling will imply that, say, you put this pan on a hot plate. Okay, and what you typically will see is the formation of these bubbles in the pan. So typically, bubble formation will happen at, as we'll study in this course at a later time, it will happen typically at nucleation sites on the bottom of the pan. But then these bubbles, because they are lighter than the surrounding fluid, they rise up through this liquid. And so when they rise up, they create an additional fluid velocities. So the fluid, as the bubble rises, the surrounding fluid comes down in its place and takes that space. So it's basically the bubble is displacing, and so it gets displaced, and you have fluid, liquid, in this case water, coming in its place. So this additional fluid motion, this churning that is created, is also classified in terms of convection. The other problem, or the other application, would be where you have condensation. Let's say you have some cooler fluid, some coolant, I would say, flowing through a tube, and let's say we are looking at condensation of moist air on the outer periphery of this tube. So you have moist air in the surrounding the fluid, very typical of air conditioners. So you have moist air, and so moist air will basically mean that you have enough moisture in the air that you can have droplets forming on the outer surface of the tube. And so these droplets actually form, and then eventually they will coalesce, they will join together, and then they will drip down because of gravity. So this is an example of condensation heat transfer, which will also be classified in convection. So latent heat exchange is also considered in convection heat transfer, since both these mechanisms also induce some form of fluid motion, or rather fluid motion is one of those aspects which is inherent to these mechanisms. So for all these mechanisms that I have covered so far, there is a basic way of describing how much heat transfer is going to take place, and that is given by what by a famous equation. And the equation says that the rate of heat transfer in all these processes is proportional to the temperature difference between the hot surface and the cool fluid or the other way around, the cooler, the cooler surface in the hotter fluid. But in this case, if I consider that the surface is hot, so I'm choosing a convention that the surface is hot and the fluid is cooler. So the rate of heat transfer will be given by H into A into Ts minus T infinity, where H is what I'll now define as a convection heat transfer coefficient. Ts is the surface temperature, or the temperature of the surface, and T infinity is the free stream temperature of the fluid. Free stream temperature means it is the temperature outside the boundary layer, outside the thermal boundary layer. So remember, in the boundary layer, the temperature will actually, or the fluid will rise or will decrease depending on which way, is the whether Ts is more than T infinity, or if Ts is less than infinity. But let's assume that Ts is more than infinity for now. So in that case, the fluid temperature will rise near the surface, but it will gradually decrease to the temperature of the free stream fluid, which is outside the boundary layer. Very similar to the hydrodynamic boundary layer, where we say that the velocity near the surface may be lower. Okay, it would be lower than the free stream velocity, which we define typically as u infinity or u naught. I don't know how you did it in fluid mechanics, but I typically say it's u infinity. So this free stream temperature is used. A is the area of contact between the contact area between the solid and the fluid. Okay, the solid surface and the fluid. So this is the rate of heat transfer. This equation, this celebrated equation, is called as Newton's law of cooling. So when you say the rate of heat transfer in convection is proportional to Ts minus infinity in T infinity, so then this is actually what is Newton's law of cooling. So let me say a few things about this convection heat transfer coefficient, which is the constant of proportionality in this model, in this law. So this value H, this heat transfer coefficient, it actually depends on a variety of factors. So H depends on the following factors. It depends on the surface geometry. So it is not the same for flow over a flat surface and maybe flow over a curvilinear surface. It depends on the geometry of the surface. It depends on the nature of this fluid motion. So whether the flow is turbulent or laminar. It also depends on the thermodynamic properties of the fluid. So, thermodynamic properties will mean in this case, properties such as, and I don't know whether I defined it or not, but let's say thermal conductivity, the density, heat capacity, things like that. So it depends on thermodynamic properties of the fluid. So clearly, it will not be the same for air and water. Okay, it will be different because it depends on the fluid itself. And the last thing that I can say it depends on is what is the bulk fluid velocity. So this basically implies that it depends on whether it is, forced convection or free convection, because as we will see later, free convection the bulk velocity is much lower as compared to forced convection. And so forced convection gives us much higher rates of heat transfer as compared to free convection. Now, though we are not in that stage at that stage, but when we were growing up, there used to be frequent power cuts, and we had this makeshift fan in with us in the houses all the time. So blowing, using a fan to regulate your body temperature, regulate your to cool yourself down, is actually a case of forced convection. But just sitting there and allowing the surrounding air to cool yourself would be an example of free convection. So please think of it this way, that what is the external way of, or the means of driving this flow, that will define whether it's forced or free convection. The other thing that you should remember is that H, this property heat transfer coefficient, it is not a property of the fluid. So you cannot use a lookup table like thermodynamic tables that we use in thermodynamics. We cannot use a lookup table to determine the value of H. Rather, it is an experimentally determined parameter. Detailed experiments, very elaborate experiments are done to measure the value of H, and it is not an easy task because it changes from problem to problem. It depends on a variety of factors, as I said, and these are not all factors. There can be more factors in the list when we do these experiments, but depends on many factors, including prevailing conditions. It is not an easy task to do, but thankfully for us, a lot of this data is already available. Our own, the book that we are referring to in this course already has lots of different empirical correlations that we can use to calculate H for a given flow condition and the nature of the surrounding fluid. So we will try and rely on that. And also in this course, we will frequently rely on the use of, when we talk about convection in this sense, we will presume that this heat transfer coefficient is somehow known. We will do some calculations, of course, of calculating the value of H, but by and large, we will assume that this is a known value. Okay, unless it's not given, where you really need to do some design calculation, and so you need to figure out what this value should be based on some data available in standard handbooks. Unless that is the case, we will sort of assume that H is known, and we will not bother ourselves with or we will not fret about where do you get these values. Okay, the last thing I want to say about convection is just to give you an example of how the value of heat transfer coefficient, or what is the magnitude of this value. Uh, what kind of numbers will we see when we do our calculations. So let me define the values based on the process that we see. So the process could be free convection, maybe forced convection. Okay, and I can also talk about convection with phase change, which would mean I'll talk about boiling or condensation. And we can then calculate, or we can then write what would be a typical value of H. The units of H are in watt per meter square Kelvin. Please remember this. Okay, and just for consistency of units, it should be in watt per meter square Kelvin, because if you look at the Newton's law of cooling, if you just look at this equation, we have Q, which is in watts. This is in Kelvin. Delta temperature difference is in Kelvin, and A is the area, which is in meter square. So clearly, H should be in watt per meter square per Kelvin. Okay. Oh, by the way, let me also say one more thing about this equation, which I forgot. I had tried. I was thinking that I forgot something. Yeah. Now I remember. So as I was saying, this equation is written in a way to explain that the heat transfer is actually taking place from the hotter surface to the cooler fluid. Okay, so the direction of heat transfer in this case is from the solid to the fluid. In case T infinity was more than Ts, Q will come out to be negative, which will basically mean, the convention that we are now using is that Q is negative. That means you are supplying heat from the fluid to the solid. Okay, so that convention should be clear in your mind, that this is the value of this value, the value of Q, whether it's positive or negative, means something. Positive value means heat going from solid to the fluid, and negative value will mean heat going from the fluid to the solid. Okay, so let's come back to these values. So for free convection, we can write values for gases and separately for liquids, because the values change, okay, depending on the choice of the fluid, whether it's a condensed liquid, or it's a condensed phase fluid, or if it's a gaseous fluid. So typically in gases, we will see that the value will be about 2 to 25 watt per meter square Kelvin, and whereas in liquids it would be about 50 to 1000 watt per meter square Kelvin. So you can already see that the use of liquids actually greatly enhances heat transfer, because now you have a higher value of H. In forced convection as well, we can classify based on the phase of the fluid. So For gases, this value will be about 25 to 250, and for liquids, this will be about from 50 to 20,000 watt per meter square Kelvin. So please spend a moment just to understand that free convection is giving us lower values as compared to forced convection. So forced convection, there's a reason why we put blowers or external fans to blow fluid over a hotter or to cool down or to heat up surfaces, because it greatly enhances the heat transfer. The motion, the bulk flow is actually one of those primary mechanisms responsible for increase in heat transfer. For convection with phase change, this is actually the most, or this will give us the highest rate of heat transfer. This is about 2500 to about 100,000 watt per meter square Kelvin. So convection, because you are looking, remember this is a latent energy exchange, so there's much more amount of heat that can actually be transferred by this simple process. So the condensation and boiling processes actually are more beneficial in terms of transferring heat. And we'll talk about these numbers will also become very important when I do some very standard, or in the next week when I do some standard calculations, or derive some methods of doing heat transfer calculations. I'll show you how these numbers become very, very critical in actually enhancing or reducing heat transfer. Okay, so this is just, so this was still for convection, that we have now so far covered convection to some basic level. More details will come in at a later stage when we do active study of convection in this course. For now, as I said, we will assume that the convection heat transfer coefficient is given. It will be presumed to be known, and then we will go ahead with those calculations without worrying about how do we calculate that number. Later we will see how this is done, how this is calculated. Okay, so we have looked at conduction now, and we have looked at convection. Now let me pick up the third mode, which is thermal radiation. And this mode is essentially, as I said, it's radiation. So this mode relates to, I think I mentioned in the last lecture, this is a mode which always there as long as temperature of a body is more than 0 Kelvin. Okay, maybe 0 degree Kelvin, thermal radiation will always be there. So that body will emit thermal radiation. So in fact, we all emit thermal radiation. When you are in a room, the walls of the room are also emitting thermal radiation. So the human comfort actually becomes an inter or a balance of all these radiation exchanges taking place. So all bodies above 0 degree Kelvin will emit thermal radiation, and the mode of this radiation or this energy exchange is in the form of electromagnetic waves. So all bodies above 0 Kelvin or at a finite temperature will emit these electromagnetic waves, which basically is the same as photons. And the reason why bodies emit electromagnetic waves is because of they're trying to it's a recalibration of the electronic configuration in the structure. So electrons basically, when they drop from a higher energy level to a lower energy level, basically will emit radiation. So we are concerned with this form of radiation exchange in this course. The last thing is, or rather, before I move to the last thing, let me also say this form of radiation exchange. It happens in all forms of matter. It happens in solid. It happens in liquids. It also happens in gases. But for the purpose of this course, we will actually focus more on solids. We will not focus on liquids and gases, because the analysis there, as I was saying in the first lecture, is slightly more complicated and cannot be covered in the first course on heat transfer. So we'll work more with radiation energy exchange between solids. The third aspect about radiation is that this is a form of energy exchange which does not require the presence of an intermediate medium, or the presence of a medium in the between two solids. So this does not require the presence of a medium. Unlike conduction and convection, conduction basically is heat transfer in a medium. A medium is essential for conduction heat transfer because you need those atoms and molecules to be able to exchange energy in a random fashion. And convection also has, you are convecting away heat, so you need another medium. You need a fluid to take away heat from a solid. Radiation does not require the presence of a medium, which means it can happen in vacuum, where conduction and convection will not happen, but in vacuum radiation will still happen. And that is the reason why I can say that we get energy, we get solar radiation from the sun to the earth, is because there's no medium, intervening medium. So all radiation reaches us, and in fact it happens most efficiently when there is no medium, because a medium tends to absorb radiation, like the earth's atmosphere. Okay, the earth's atmosphere actually absorbs radiation which is incident. So on the outer surface of the atmosphere, the radiation is the highest, which is about 1400 watt per meter square. So it absorbs this radiation, and by the time it reaches us, the radiation intensity is actually much reduced. So it happens most efficiently in a system where there is no medium. Okay, but what we'll assume now in this course is that, for most parts, towards the end, we'll discuss a little bit about how this gets absorbed. But then, for most parts, we'll assume that even if there is a medium, let's say air, when we talk about radiation exchange in a room, there is air. I cannot assume it's vacuum, but then we will make one assumption, a simplifying assumption, that the medium is not absorbing this radiation, or neither is it emitting radiation. So that will be one simplification that we will make to work on these kinds of problems. Okay, now one more thing is that, this radiation is actually, it's a volumetric phenomena, because every particle in the solid or any medium can actually emit radiation. But since we are dealing with solids, and we will deal specifically with solids that are opaque to thermal radiation. So since we will deal with solids that are opaque to thermal radiation, and by the way, what do I mean by opaque is that these solids will not transmit radiation. So there is no transmission. So when a radiation is incident on a solid, it can either reflect it or it can absorb, but it will not transmit. Okay, like you can say glass is one of those things which can actually transmit radiation, but we will not talk about, or transmits light, for instance. So, but we will not deal with these kinds of materials. Not that glass is not there's a what I'm talking about is thermal radiation, not incident light. So there's a big difference there, and we'll discuss that at a later time. So solids that are opaque to thermal radiation, what they do is the radiation tends to end up being from a volumetric phenomena to a surface phenomena. So it becomes a surface phenomena, which basically means that the thin layer on a solid, the thin surface layer on a solid, is what will actually absorb or emit radiation. We will not be worried about what happens in the interiors, in the bulk, because there the radiation is anyway not going to reach, is not going to escape out from the surface. So whatever radiation even the internal matter provides, it gets absorbed within the solid itself. Okay, so it never reaches the surface. So we'll only be concerned with the thin layer, and that is why we will talk about it as a surface phenomena. Okay, the surface itself, the surface is what is going to emit radiation. So how radiation or the basic theory of radiation goes something like this. Let's consider that we have a surface which is at some temperature, again I'm going to say Ts. So this surface can actually will emit radiation because of a non-zero temperature, and what it emits, which I'm going to denote as E. Okay, this is the emitted thermal radiation. Okay, this emitted thermal radiation, which is in watt per meter square. So it's basically radiation intense, radiation, or say heat flux that the surface emits. So there is a maximum limit to this heat flux. The maximum limit is given by sigma times the surface temperature raised to the power 4, which is also called as radiation emitted by a black body. I'm going to say EB. So this is radiation emitted by a black body. And what is a black body? A black body is one, or we call something as a black body when it is a perfect emitter, or it emits. A black body is one which emits, it is a, let me not say emits, but let's say it's a perfect emitter. So when the, if a surface is at some temperature, if the radiation being emitted is given by sigma ts to the power 4, we will call that as a perfect emitter or as a black body. So this is the maximum limit that some surface can emit. But actually real surfaces will emit something less than this. So what I was saying is that in the case of a real body, what you will see is that the emitted radiation E, which is for a real surface will mean that, in general, I mean, I should not say that a black body is not real, but a real surface which will have emission which will not be the same as the maximum emission. So this will be some epsilon times sigma ts to the power 4. So a real surface will emit radiation which is lower than what a black body will emit. Epsilon here is what we call as emissivity, which is a value between 0 and 1. And so emissivity denotes the, I should say, the efficiency, or it denotes how efficiently a surface emits radiation related to a black body. Okay, so that is emitted radiation from a surface. Radiation need not be all because of emission. We can also have radiation incident on a surface. So if I consider again that same, a surface which is maybe emitting some radiation, there could also be incident radiation to the surface, which we call as G as a symbol, and G is what we call as irradiation. So this is radiation incident on a surface from other surfaces or a medium. So this is incident radiation, which is what we call as irradiation. Now, when you have incident radiation on a surface, this incident radiation can, as I was saying, that it can either get reflected or it can get absorbed. In special cases, it can also get transmitted. We are not worried about transmission yet. But typically, we will talk about incident radiation getting reflected and absorbed. So I can write that the absorbed amount of radiation, so GABS, let's say with the subscript ABS, is actually going to be G, some alpha times G, where alpha is what we call as the absorptivity. So alpha denotes sort of, the uh, portion of incident radiation that is absorbed by the surface. So alpha again can only be between 0 and 1, cannot be more than 1, and it cannot be negative. Okay, same with emissivity. Emissivity cannot be negative. So that is the absorbed radiation on a surface. And an important part is what happens when the radiation gets absorbed. You can imagine that because radiation is getting absorbed, the surface essentially is absorbing this energy. so its temperature should rise, or it should, it should have a higher temperature. But it's also emitting radiation. So the temperature of that surface or of the body depends on the interplay between this incident radiation or the absorbed radiation and the emitted radiation. If your surface has incident radiation, that doesn't mean it cannot emit. It will still emit. Any as I just keep this in mind, that G is not the net resultant. It's basically incident. E is emitted. So there is a key difference between the two. More importantly, alpha also depends on the nature of this irradiation. So what I mean by it depends on the nature of irradiation is that if you look at, let's say, if I have a surface, okay, maybe some ball, or maybe some cylinder, or whatever it could be, a plate, the absorptivity of that surface to, let's say, solar radiation, let's say alpha of that surface to solar radiation, let's say if I keep it out in the open, and I allow it to absorb solar radiation, this need not be the same as alpha of the surface to maybe radiation received from a furnace. So if I keep this surface in a furnace, it need not be the same. So alpha is not just one value that for a surface. It actually depends on the nature of irradiation. So what is the nature of irradiation? What do I mean by nature of irradiation? Is that it depends on the spectral properties of the radiation. Spectral properties would mean that it depends on the wavelengths at which the radiation is being received by the surface. Okay, so the nature of this G, at what wavelengths, because this G is just sort of like a whole sum of many different aspects. It depends on the wavelength, it depends on the temperature of the of the thing that is emitting that radiation. So that is the reason when we talk about alpha of solar and alpha of furnace. So for instance, solar radiation emits or is emitted at about 5800 Kelvin. A furnace may be operating at 1200 Kelvin. So these need not be the same. Okay, they may be the same, but in general they're not the same. So when we talk about alpha, we have to determine alpha by looking at the source of the irradiation. So please keep also this in mind, that this is not going to be so simple to just have one given alpha for a surface. Now the last thing I want to discuss, and maybe I think we might be able to close the class early today as well, uh, is a special case of radiation analysis which you have done in JE, and which I'm just going to touch upon today. But when we talk about radiation later, we will do this in much more detail. Uh, so let's look at this particular scenario where I have a surface. Let's say I have some surface at temperature Ts. Let's say the surface has area A. Sorry, surface is area A, and it has an emissivity of epsilon. So somehow these values are known. Okay, the area is known, temperature is known, the emissivity is also known from some different measurements. Let's say it's kept in a large surrounding space. And what I mean by large surrounding space is that you can imagine that the universe is only this surface and the surroundings. There is nothing else in the universe for this surface. It only sees this surrounding. So this surrounding is maybe at some temperature. Let's say T surrounding SUR. Okay, there is a there may be a medium. So either the intervening space is filled by is vacuum, or there is a medium, but the medium is not does not intervene with radiation. So it does not intervene with radiation, which basically means that if these two surfaces are emitting radiation, the medium is not going to absorb that radiation. So whatever emission leaves from one surface, it goes to the next other one. Whatever goes from the other one comes to this one. Okay, so the enclosure is much larger. You remember this. The surface is small as compared to the enclosure. Okay, now in this scenario, we typically make one assumption, and the basis for that is that assumption I will cover later when we talk about radiation. An assumption that is made is that the surface, or let me say the surface, is assumed to be a gray surface, and it's not the gray color, but it's assumed to be gray, which is a property of a surface. And a gray surface is one in which the absorptivity is the same as the emissivity. Okay, so we'll prove how this comes in. This is a very famous law as well, but for now let's say the absorptivity is the same as the emissivity. In that case, I can calculate the radiation, the net radiation, or the net amount of heat transfer from this surface to the surroundings. So we can write that the net rate of radiation heat transfer, net rate of radiation heat transfer, and I'm going to be very uh, I'm, even though I'm saying it in a very subtle way, I'm going to say it's from the surface, which is I'm saying is Q. The net radiation, and let's say Q radiation, because we are doing this for a very special case. So the net rate of radiation heat transfer from this surface to the surroundings, okay, which I'm going to write as K radiation from, because I'm saying the surface is going to emit, it is going to have emission, and it is going to there's going to be net rate of heat leaving from the surface. Now the reason I'm saying this is that because there is a large surrounding which is also at a finite temperature, so that must also be radiating, thermal energy. So that radiation, if I look at this sketch now, let's say incident radiation is coming in the form of this irradiation G on the surface. This surface itself, maybe if I use a different color now, is emitting at E. Okay, but I also know that the surface can absorb this incident irradiation. So if I look at the a basic energy balance on this surface, okay, I can say that if Q radiation is the net rate at which heat is leaving from the surface, it should be the difference of what the surface is emitting, okay, minus what the surface is receiving. So what is the surface receiving? It is receiving alpha times G, because it's actually taking that heat in. And of course, because we're dealing with the areas, I will multiply this by the area of the surface. Okay, so it's receiving. So if we want to be clear about this, this is uh, energy leaving, and this is energy absorbed by the surface. So net rate of radiation exchange will be the difference of what is going out minus what is coming in, and of course multiplied by the area, because these radiation, yeah.
Sir, are we talking about the rate of heat transfer or the amount of heat transfer?
No, we're talking of rate of heat transfer.
Like the formula you told before, also they were all on heat transfer.
Yes, it's always the rate of heat transfer. It is not the total amount of heat transfer. So I think your question is whether we're talking of quantities in watts or in joules.
Yeah, yeah.
Yeah. So we are all in heat transfer. Remember, we never talk about in joules, because joules would mean that the system is already reached to an equilibrium state. We are dealing with non-equilibrium systems.
Hmm.
So it's always energy in transit. It is rate at which energy is flowing.
Okay, okay, sir.
Okay, so it's always in joules per second or watts.
Okay, sir.
Okay, yeah.
Yes.
So I'm still talking of this rate of at which, so I have written, so if you see this, there is a rate here. So I'm talking of rate of radiation heat transfer. I'm not talking of how much heat will be totally exchanged. I'm saying at a given instant of time, this is the rate at which this is the net rate at which the surface is giving away energy. Okay, on a per unit basis, per unit time basis. So Q radiation is E minus alpha G into A. Now remember, what is E? E is the energy emitted, which should be epsilon times the energy emitted by a black body at the same temperature. So that is epsilon sigma Ts to the power 4. So for a real surface, we will have emission which would be slightly lower than what a black body emits. So, and what is G? In this case, the key assumption that I've made is that the enclosure is a very, it's a large enclosure, it's a large surrounding. So as we will see later, in such a scenario, when we say the enclosure is large, it typically means that it behaves like a black body. So G becomes sigma T surface to the power 4. It's a even though it may be, very far away, but it's still a large surface. So all radiation that it emits, and it basically absorbs all radiation, and also so it emits as a perfect emitter. So it becomes sigma Ts to the power T surface to the power 4. And now if I write this equation Q radiation, and let me write the flux, in fact. So let's say Q double dash of radiation, which would be Q radiation by A. This will be epsilon sigma Ts to the power 4 minus alpha sigma T surface to the power 4, except alpha is the same as epsilon because I said it's a gray surface. So we can write this as epsilon sigma Ts4 minus T surface to the power 4. So that is a flux because of radiation exchange between a surface and its surroundings, which is what, as I was saying, is something that you would have, used maybe in during JE. At least I remember using this. I don't know. We were taught this in maybe 12th. But there are key assumptions to it, and we will visit these assumptions when we talk about radiation in greater detail. So anyway, this is the net rate of radiation exchange between two surfaces, one being at temperature Ts and the other being at temperature T surface or T surroundings. Okay, so do keep in mind that when we write this equation, we are actually saying that this is the net rate of radiation leaving this surface that we're dealing with, the surface Ts. So clearly, this must be the radiation net rate of heat exchange, or net rate of heat being absorbed by the surroundings. Okay, so there is no loss. So whatever goes, the surroundings must be absorbing this much radiation because the surface is giving away this much energy. Now, in many applications in heat transfer, and especially when we talk about conduction analysis, we might be using a little bit of this aspect. Remember that in convection, we said the rate of heat transfer, that's in convection, we said is, or rather flux, is H times, let's say, Ts minus, I don't know, T infinity, right? This is what we had written in Newton's law of cooling. A similar idea is also used in radiation, where we can write Q double dash radiation as some heat transfer coefficient associated with radiation times Ts minus T surroundings. And the reason this is done is because it is, as you will see, this delta T Ts minus uh, T infinity, as I'm saying, or Ts minus T surface, as I'm saying, this will actually have a key meaning in all form of conduction analysis. Okay, even though it's to do with radiation, but this will actually have a key role when we do very basic conduction calculations. So it becomes sometimes useful to write the radiation heat transfer in terms of just a delta T. But what it does is, now if you compare this equation with this equation that we've derived, it is clear that HR must be equal to epsilon sigma Ts plus T surroundings times Ts square plus T surrounding square. So the radiation heat, if I can say the radiation heat transfer coefficient, it actually becomes a function of the temperature itself, which is what is slightly more cumbersome and more difficult to handle when we are solving for any of the unknown temperatures. But it becomes useful to sometimes write it in this way. Now I remember what I missed saying. Okay, what I was about to say is that I didn't mention what is sigma. I think you all assume that and rather I assume you know, but let me say this: sigma. Oh, by the way, this way of writing it is what is known as a Stephen Boltzmann law, and sigma is a Stephen Boltzmann constant, which has a value of 5.67 10 to the power minus 8 watt per meter square, because it's per unit area, and Kelvin to the power 4. I was thinking I forgot. So, but I know that, I mean, I'm sure that you know this already. So, but just to reiterate and just to make sure that we are clear on this. So sigma is a Stephen Boltzmann constant. Okay, coming back to what I was saying about this thing, HR. Yeah, so the reason we write this is that when you have, let's say, a scenario, let me take one scenario now just to explain what this will do. Let's say you have a solid surface which is at some temperature Ts. Okay, there is a fluid surrounding it which is flowing over the surface. So let's say the fluid has a heat transfer coefficient H, maybe temperature is, I don't know, T infinity. Okay, and there is also a surrounding surface which I can draw like this, which is much larger as compared to the surface that we're dealing with. So let's say this is at some temperature T surroundings. Okay, and has a much larger area as compared to the area of the surface, which I can denote as has some area A. The surface also has some emissivity epsilon. So in this case, when you want to write the rate of heat transfer, so the heat transfer is not just because of convection now, it is because of both convection and radiation. Okay, so the net rate of heat transfer now in this case will be a combination of the mode heat transfer because of convection plus heat transfer because of radiation. So we will have to write that the net rate of heat transfer from the surface is HA Ts minus T infinity plus, I can write this as epsilon A sigma, assuming that the surface is gray, Ts4 minus T surrounding 4, where I can also make one simplification now, that if, let's say, I said the surroundings are the same as the temperature of the ambient fluid, if, then I can write that Q will be HA Ts minus T infinity plus epsilon A sigma Ts minus T infinity times Ts plus T infinity times Tm square plus T infinity square, which I can write as some H combined, let me say CUMB, times area times Ts minus T infinity. Right, so this H, as I'm saying H combined, is actually the overall heat transfer coefficient, if you can say it. So this becomes H plus epsilon sigma, not A, sorry, epsilon sigma uh, Ts plus T infinity Ts square plus T infinity square. So in many problems that you will see in your textbook or any other source, you might see that you have both modes of heat transfer taking place, or the boundary condition that you will be tackling will have both modes specified. So in that case, it becomes sometimes easier to do our analysis in this manner. So this is what we will use sometimes to denote the total rate of heat transfer when both conduction and right both convection and radiation are uh, are possible. I mean, if we can ignore one, that's great. But if we cannot ignore, then we will have to go ahead with this kind of analysis. Okay, thank you.